Yes, it is Thursday, the 18th. And then it's going to cover chapters 1 through 3, right? Chapter 3 is the resonant, right? The soft switching, right? Yes. Okay, chapters 1 through 3. And then, yeah, this time I'm going to have it open book instead of asking you to prepare one sheet, 8.5 by 11. It's online anyway, so I'm just going to have it as an open book, open notes, test. And it's going to be synchronous, just like in EE411, same way. We'll talk more about the procedure or the details on the exam next week. Okay. So go ahead and mark your calendar. Midterm number 1 is going to be the 18th of this month. Okay. Any questions? All right. If not, let's continue our discussion on chapter 3. We're almost done with this second one. I want to get to the third one today. So here we have the zero voltage switching resonant buck, right? And we talked about the 4 different states already, right? And how zero voltage switching is achieved, right? By simply putting the switch in parallel with resonant converter, resonant capacitor. There you go. The key there is that if I could somehow have a state in the circuit where the circuit resonates, right? We have a resonant circuit, then we know that voltage across this cap will be sinusoidal, right? And if it's sinusoidal, and at some point of time, that voltage will reach 0, right? 0 volts. And if it hits 0, if you could somehow clamp it, and we can see we can clamp the voltage through this diode, right? Then if you can do that, then we can turn this switch. Was it off or on? I don't remember now. Turn the switch on. Yeah, turn the switch on at 0 voltage. Okay, so that's the key, right? As you can see right there, by placing these 2 components. Now you know the purpose of placing these 2 components in parallel with the switch. One more time, the capacitor is there to provide the sine wave voltage, and the diode is there to clamp the voltage once this sine wave voltage tries to go negative, right? So it's clamping it to 0, and therefore keeping the voltage across the switch 0 as well, because they're in parallel. And that's the perfect timing for us to turn on the switch, okay, at 0 voltage. All right. So 4 different states, and we talked about the KVL, KCL, I believe, right? And then we look at the waveforms as well, right? And you can see that the inductor current is being clamped as well to I out right there, right? So that's that would tell us what the max current, right, through the inductor, which is going to be that I out. Okay, and then, well, actually, no, I lie. The max current, right, you have to compare between these 2, right? So whichever one is the worst, that would determine the saturation rating of that inductor. Okay, so you need to find the worst out of the 2. Sorry about that. I almost forgot that we have another peak current right there. So determine which is the biggest or larger magnitude-wise. Then that would determine the saturation current rating of that inductor. All right. Another thing is that I don't know if I did this on Tuesday or not, but we also have the peak of the capacitor voltage, which occurs when inductor current is equal to 0, right? This is during resonant mode, as you can see. That's a sine wave, and there's also a sine wave. And that happens why? Well, because when IL is equal to 0, right? That means what? That means IC is also equal to 0, right? Because they are in series. If you look back to this resonant state, you can see that they are in series. So IL is the same as IC. So whenever IL is equal to 0, that means IC is also equal to 0. I'm not going to write this down because I think I did last Tuesday, maybe, I don't remember, but by now you should know that IC is equal to C dVc dt. So therefore dVc dt is equal to IC over C, right? And IC is equal to 0. So therefore dVc dt is equal to 0, right? So if the slope is equal to 0, that means that's a, what do you call it? That's indication that voltage across the cap is reaching its max right there, okay? And then we also have the max on the minimum swing on the inductor current right there. When it swings negative following a sine wave, you can see it reaches its mean value. And that happens when, you can see when capacitor voltage is equal to Vs right there, right? So that minimum peak right there occurs when, minimum peak on the inductor current occurs when capacitor voltage is equal to Vs. Does that make sense? Well, let's see. Again, that's the resonant mode right here. Right. So what happens when Vc is equal to Vs? If this is equal to Vs, then you can tell from KVL that voltage across the inductor must be 0, right? By KVL, right? So and we know that voltage across the inductor, VL is equal to L dIL dt. So therefore, dIL dt is equal to 0. That means the slope of the current, inductor current is equal to 0. That tells us that the inductor current is reaching its peak value, in this case on the minimum, on the negative swing right there. So this makes sense to me as well. Okay, and then another thing is that this critical point right there, T2, is when capacitor voltage reaches 0, right? And then that's when we have capacitors fully discharged. This capacitor is fully discharged, right? So it's 0 volts, right? And current can no longer flow through here, right? But inductor current, I should say, right? It can no longer flows there because there's no more energy or charge left in that capacitor. So therefore, the negative current now will have to flow through the diode, right there. So that's when the resonant mode changes to non-resonant, right, to here. And then since diode is conducting, that means that, assuming ideal diode, that means that voltage across that diode is equal to 0. If the voltage across that diode is equal to 0, that means voltage across that switch is also equal to 0. That would provide us with a good condition for turning on that switch. So as the diode is conducting, imagine if there's a diode there, right, and it's conducting, it's a short, we are turning on the switch, right? So now the switch is on. Now at this point, keep in mind that even though the switch is on, it's not conducting current yet, right? Because current is negative, right? And the switch can only handle positive current, right? If you look back here, the switch is unidirectional. It can only provide a path, provide the path for the current to flow from left to right that way. But at this point, at this moment, current is still negative, right? How do I know that? Well, from the waveform, right? If you look at the waveform back here, right, you can see that when capacitor voltage goes to 0, current is still negative, right? Still below 0. So that tells me that current is still flowing from right to left. So therefore, this portion of the current right here, from here to here, that's the negative current through the inductor. That must be flowing through capacitor, right? And this is the segment of time, right, between here and here, right, between T2 and the 0 crossing right there, right? So during that time segment is when we want to turn on the switch, right? Why? Well, because again, diode is conducting, right? So voltage is equal to 0. So now if I turn on the switch during this time, this time segment right here, then I would be able to turn it on at 0 voltage, right? And again, going back to here, as long as the current is negative, even though the switch is on, it's not conducting current yet until current reverses itself, right? Swings positive. If that's the case, then as you can see, diode cannot provide that path because diode is pointing to the left. So if the current if current through the inductor wants to swing positive, then it could, right? As long as the switch is already on. And in this case, yes, the switch is already on. So now the switch is taking over the current into the inductor that way. Okay. Whoever found this is clever. I don't know who found this, invented this converter. To me, it's just clever to be able to figure out, how to play with the currents, how do you time the switch and so on and so forth. Like how do you place the components to create this, soft switching. Okay. And then now that the switch is on, current is flowing positive in the positive direction, right? Switch is on right now, so current is through the switch. And that current, as you can see from this KVL right here, right, should be linearly increasing. Why is that? Well, because we have constant voltage across the inductor, which is Vs, right? This is 0, that's 0 across the switch. So voltage across the inductor is Vs, constant. That means Vs is equal to L dIL dt. So the dIL dt is equal to Vs over L. And so therefore it's a constant slope, positive constant slope, which tells us that inductor current grows linearly, right? As you can tell from the waveform right here. Right, from the waveform, it grows linearly. Until when? Well, until that current grows to I out. Right, so this current keeps increasing while this current is decreasing, right? And as soon as IL is equal to I out, then this diode turns off by itself, right? And IL cannot be higher than I out. Why not? Because there's no other path, right? Besides that diode. That's why it's being clamped. This inductor current is being clamped at I naught. So at the time when IL is equal to I naught, the circuit state changes from D to E, right? When the diode is off and the inductor continues to conduct I out, just like that, right? When that happens, then the equation would be trivial because I know that voltage across the cap here is 0 still because that's in parallel with the switch, and inductor current is just I out. Okay. Any question on this? And how do we determine the maximum switching frequency? Well, that will be determined by the switching period, right? The limit on the switching period. You can see that that last state, right? You can leave it. You can leave that state, to continue freewheeling the output current through the inductor until the next time I turn the switch off again, right there. See that? Once I turn the switch off again, see from this pulse right there, pulse now goes down. That means turn the switch off. Then we repeat the cycle from the beginning, right? So from there, I can see that that I could actually push the time at which I turn the switch off again, this T basically, right? I can shift this T, capital T time to the left, right? And by doing so, I'm increasing the switching frequency, right? Remember that period is the inverse of switching frequency. So if you are moving this period to the left, that means you are increasing switching frequency, right? And you can see that there's a limit on how far you can move this T point into the left, right? And that limit is T3, as you can see. It cannot go beyond T3. So therefore, T has to be, switching period has to be larger than T3, right? Or if you do frequency is the inverse, right? So therefore, switching frequency must be less than 1 over T3. You agree with that statement?
Yeah, that makes sense.
Okay, good. All right. Now, the rest is going to be equations, right? I'm not going to go through this. We've gone through this, except now I'm explaining or presenting this in more details, right? But you already know the equation that we talked about earlier, or also on Tuesday, right? When you have the first state, right? You do KVL, KCL. What do you get for voltage across the inductor? What do you get? Not voltage. What do you get for current through the inductor? In this case, it's trivial, right? For state 1, because IL is equal to I out, right? But VC is going to be equal to VS minus VX, right? And we already established that VC is increasing linearly, right? By doing this. So that's the equation that shows or demonstrate that VC is increasing linearly with time. That's a linear equation right there. All right, and just like the previous circuit, once you get the equation for capacitor voltage with respect to time, then we start looking for the equation for the times, right? For the timings, T1, T2, and T3. Right? For T1, you can get it from equation number 11. We know that at T equals to T1, what happens there? When T is equal to T1, VC is equal to VS, right? I believe. If you go back to the waveform right there, at T is equal to T1, the unique condition of that is that VC is equal to VS right there, right? So you set VC equals to VS and then solve for T equals to T1, right? So I'll let you read through this yourself, similar to the previous circuit, right? In terms of the approach to get the times, right? So there, oh, no, not that one. I believe it's this one, yeah, right there. So find VC at T1, which is equal to VS, and then solve for T1. And T1 right there, right, is equal to CR over I out times VS. Notice that just like in the previous circuit, this time T1 is a function of I out, right? That times T1 depends on the output current. So if you change the output current, then T1 changes. Typically CR, not typically, but CR is fixed, it's fixed value. It's a fixed value. VS typically is a fixed value, right? So the only thing that would change T1 is if you change I out, which usually that's what happens, right? In real world circuit, you change the load, that means you are changing I out. As you are changing I out, you are changing T1. Okay, and does that make sense from the waveform? Well, let's see. Imagine if you're changing I out right there. Let's say you are shifting I out to a higher value. Then you can see if it's higher value, then where is it? All the way, oh, all the way there, right? Then let's see. It's actually not that clear. Looks like because we're looking at inductor current, but the way the circuit state changes by VC equals to VS. However, you can see that the peak of these voltage is a function of I out. That's what did it. That's what changes it. Imagine if this peak is higher, right? So that means it takes longer. Sorry for the bad sine wave. You know, I'll use my.
Is it the same effect as increasing the resonant inductance?
I out, no. I out by itself is not going to change the inductance. Inductance is going to be fixed. Like you.
Or I mean, would altering the inductance like have the same impact on the switching frequency? Or it would be a square root relationship, right? Because Z naught is.
That's right, but we're not changing Z naught, right? Because those are fixed value. That is LR and CR. Those are the value that you have to select when you build this circuit. So these are all fixed values.
Or we just generally don't select the load, or like the load can be kind of variable.
Of course, yes, exactly. Right. So if you connect this supply, the power supply to a load, then this load could change current, right? So out of these three, I should erase that. Out of these three parameters, VS, I out, and Z naught, the only one that's going to vary is I out, most likely, right? Z naught is not going to change. VS could, right? Because typically input voltage also fluctuates, but I think in most cases Vs almost constant. But the one that's gonna vary a lot is I out. So if you imagine I out is higher, that means the peak is also higher, right? So it takes more time for the sine wave. How do you draw that? I don't even know how to draw this.
Also, wouldn't the initial linear slope be steeper? Because if you have more current going through the capacitor, then you're going to have a faster change in voltage. Like, wouldn't it be steeper than the red one?
Yeah, let me see. The slope is a function of I out. Exactly. Right there. You're right. Yeah. So that's what I was trying to draw. Right. It's a steeper current, a steeper slope. So no, steeper means the other way around. Sorry, that's the wrong way. Steeper means faster, right? So like that. Looks like. Oh, look at that sine wave. Beautiful. So you can see that the T1 changes, right, as you are increasing the load. Okay. Now, does that make sense? Let me see. As you increase the load, I have actually never checked this. So this is the first time I'm checking. Oh, it is true. That's awesome. Look at this equation. T1 is inversely proportional to I out. So as you increase I out, T1 is getting faster. That's what we are seeing, right? Is that from the previous equation, the slope, if you look at this from the slope point of view, as you are increasing I out, the slope gets steeper. Right? That means faster, right? Faster slope for VC. Faster means steeper, right? Right here. So the blue that I just drew, that's steeper slope than red, right? So it's faster rise to the peak value. And because it's faster, that means because it's growing faster linearly, that means it reaches VS faster as well. So the new TS, the new T1, what did I say TS? The new T1 will be shorter or faster than the old T1.
Wouldn't T2 stay the same though, because the resonant frequency doesn't change? Or it wouldn't be exactly the same, it would be because it would be shifted due to T1's change.
Exactly.
But because it's resonant, like wouldn't it be
right.
Shift T2 by the same amount?
Yeah, T2, I don't know if by the same amount, but T2 will also have to move to the left, and so will T3. But that's something that you can look prove using mathematical equations, right? When from the picture, yes, it makes sense that as you are shifting T1, then you are shifting T2 and T3 as well. But in order to prove that, you need to analytically, you need to get the mathematical equation. So we'll get to there, right? We'll see if T2 is inversely proportional as well, right? Okay, so that's the equation for T1, right, that you would need to find average output voltage later. And then Vx is, what is Vx? Vx is the voltage across the diode, right? Right there, right? And why is this important? Well, because that's gonna define our output voltage, because it's sitting right across the load, therefore Vx is equal to V out, right? That's why I need the equation for Vx, because later I'm gonna have to find the average of Vx to give us the average of V out.
Wait, Professor?
Yes?
Isn't there an inductor sitting between, like that current source just models an inductor, right? And the inductor lies between the load and the diode.
Yep.
So wouldn't the load voltage be a little bit different?
Well, in this case, the inductor doesn't matter because the current through it is constant. So therefore,
or the other inductor, like the current source models an inductor in series with the load and capacitor.
Yes, exactly. So I see what you're saying. So you have the diode, and you have the inductor, and you have the capacitor, right? Just like that. Is that what you're saying?
Yeah, exactly.
Yes. So this box right here, that's a low pass filter, isn't it? You agree?
Yeah.
So what does a low pass filter do to the input voltage? This is your input voltage to the low pass filter, and that's the output voltage to the low pass filter. So low pass, go ahead.
The capacitor voltage never hits zero then, right? Like when the diode's not conducting, doesn't the current source sit behind kind of the load resistor?
Say it again. That second part, I missed that.
So like when the current source models like the inductor, right?
Mm-hmm.
So it'll try to keep the current fixed going through the load.
Mm-hmm.
And so when the diode voltage hits zero, won't the I out will still be maintained going into the load. So it wouldn't hit zero when the diode voltage hit zero.
When the
when
diode
you're referring
voltage,
to the load voltage, are you referring to like before that low pass filter?
I'm referring to this as well. Yes, right now I'm looking at this voltage. You're right? This Vx is actually right here, Vx. But that's why I was asking earlier. What does LPF? What does the low pass filter do to this Vx?
Oh, it removes the change to zero, so it maintains whatever voltage.
Or in other words, this right is averaging function, right? That's what low pass filter does to a voltage. It's averaging it. So if you have a voltage that looks like this, input to that filter, then the output would be if I use red, it will be more flat, right?
It's like a running integration, right? To some extent.
Exactly. So it's to me, it's just an averaging function. To me, this low pass filter is just averaging the input. So if you have a square wave, then the output will be more flat, right? Because it's low pass, right? It gets rid of the high frequencies. This is high frequency right there. The steps, those are high frequencies. So the output does not see high frequencies anymore, right? It's more like a DC. So that's the output. Make sense? So when I say averaging Vx, that's the same as averaging across the diode voltage. That's the same as saying there's a low pass filter after this Vx. That's going to give you V out.
That makes sense. We're just like examining before
Yes.
the signal that's being filtered.
Yes. So what I'm saying is that V out is the average of Vx, which is true in the actual circuit. If you put back all the components, LC, that's what it does anyways, right? Okay. So right now I'm looking at the waveform across Vx. If I can average it, and then that's gonna be the same as our V out. Does that make sense?
Yeah, that clears it up.
Okay. All right, let's see. So that's our T1, and then the second interval or second state, we have the resonant, right? And this is where you have to do the differential equations. I won't go through that anymore. You can go through this yourself, and at the end, you get the equation for IL, which is a sine function, as expected, right? And also VC, which is also a sine function. Where is VC? Right there, as expected, right? Because we have resonant circuit, IL should be a sine wave, VC should be a sine wave, and that's the proof right there, right? And from here, I can say that IL, peak value of IL is equal to I out, right? And then peak value of VC is equal to what? Vs plus I naught Z naught, right? You agree with that? Now, remember, we have this discussion for the first circuit that you have to have the right offset to make this work. Same thing here, that Vs plus I naught Z naught, right? You got to be careful on the offset. In this case, the input voltage. Let me erase this, it gets so crowded here. Right? Look at, focus on the capacitor voltage. If I'm not careful on the input voltage, then it is possible that I won't get any resonance, right? Any zero current turn on for the switch. Imagine if I'm not careful, then the offset's going to be even higher. And then the sine wave doesn't go to zero. I mean, it tries to go to zero, but then before it even reaches zero, it bounces back, right? Like that, to make the full sine wave. So if that's the case, then this circuit no longer works, right? Because it's just going to keep oscillating like that. Right? So
it's limited by I out?
It's limited by both, actually, VS and I out, right? You can have the same VS, right? You can look at it from the VS point of view. And if you say, okay, I have a fixed VS, then you can ensure that this happens right here by making sure that the peak right there is always larger than VS, right?
So that's one of the homework problems, right? So one of the homework problems says to find like the maximum or the minimum like load resistance. Is that how you would go about that? Or would you use the switching frequency 1/T3 relationship, or either?
No. What was the question first though? What was it again?
So I was having trouble on the first homework problem because it asked to find like the maximum load current.
Yes.
And would you do that based on that relationship right there to ensure it can reach zero? Or do you do it based on the switching frequency? Because we're given the switching frequency.
Yeah, I don't think there's I don't think switching frequency would answer that question, because it's asking
for the 1/T3. Oh wait.
Right, that's different, right? That's like because the question asked specifically on what condition of output current, right? Am I right?
Right.
Yeah, so that relates to I out. So that's the condition that you need to apply, is that I out has to be larger than VS over Z naught.
Oh, okay. That actually makes sense.
Yeah. Make sure that this inequality is correct. Sometimes I get this mixed up. Let's see, the peak.
Or less than? I out should be less than VS over Z naught, right?
No, this first one.
Bounded by a minimum, like it has to be below, I think.
No, let's see. See, if this peak right there is less than VS, then it's going to bounce back. Right? If this peak right there is too small, right, let's say over here, then it's going to bounce back. So we want to keep this peak right there, peak of the sine wave, to be larger than VS.
Oh, I gotcha.
Am I right on that one?
Yeah, so there's also a maximum. I out is bounded by minimum and maximum.
Yes. So in that case, then I out must be larger than V out over VS over Z naught. There you go. So that's the condition.
But you couldn't just have like an infinite I out, or like
infinite I out? No.
Because it would be larger than VS or like really large.
It's going to be really large, yeah. And what would be the implication of that? If it's very large, then this is basically a step, right? Just remember, I out, the larger the I out, the steeper the slope, right? To the point that it's going to be very hard for you to time, because it's so fast, basically.
And that's the T3 constraint.
Yeah, that's the T3 constraint. Yes, T3 constraint, right? The T3 right there.
Oh, T3, that's right.
Yeah. All right. So theoretically, yes, you can have a large I out, infinite I out, but then the trade-off will be your T3 is going to be so tiny, right? Your T3 is going to be so fast that, imagine if T3 is so close to zero, then how do you time T1 and T2? And how do you actually practically, turn the switch on, right? It's going to be tough to do.
That would be limited by even like the switching speed of diodes and stuff like that.
Exactly. That's what I'm saying, yes. Yes, it's not practical to do so. Theoretically, on paper, yes, you could, but in reality, it's going to be impossible, right? Because of the time it takes to turn on and turn off the switch. All right. Okay, is that good?
Yeah, everything's all clear.
All right. Okay, next, timing, right? Timing for T2. It's also from here, right there, right? So that's the, how do I do that? Is by applying the unique condition at T2, or what was the unique condition at T2? That's when VC is equal to 0. So you get the equation for VC right there, and then set it to equal to 0, and then solve for T2, right there, and that T right there. Then you get the equation for T2 right there. And then as expected, remember I said earlier that if you shift T1 to the left, right, as you increase I out, then this is the mathematical proof that I out is also inversely proportional to T2. So as you're shifting T1 to the left, T2 will also be shifted to the left. Right? It's not linearly proportional, as you can see from the equation. So it doesn't mean that if you're moving T1 to the left by 10%, it doesn't mean that T2 will be shifted to the left by 10%. It's not linearly proportional, as you can see from this equation. All right. And then this next state, that's when we have a non-resonant state, right? Here we have simpler equations because VL is equal to VS. So that's just going to be linear change in the inductor current, right? That's the slope right there. And then it's going to continue until T3, right? So you have VL, you have DIL dt equals to VS over L. And from there, you should get the equation for IL. Keep in mind that at this point, VC is equal to 0. It's already fully depleted, right? So VC is equal to 0. Only IL is still in action. So IL, the equation for IL is this one right there, right, with the initial conditions. And then from here, I can solve for T3. So this T could be changed to T3 if you plug in T3 there. And we know that at T is equal to T3, IL is equal to I out. So if you replace it with I out, solve for T3, you get this equation right there. Now this is interesting because look at I out equation, look at T3 equation. T3 is actually increasing with I out. It's not inversely proportional. That is interesting. This is the first time I actually noticed this. So T1 and T2, as you move T1 to the left, looks like T2 moves to the left as well, but T3 looks like it is not, based on this equation. Okay, based on this equation, it actually moves to the right. However, I almost forgot. There is T2 there. So this T2 actually moved to the left. So overall movement will be to the left, in my opinion, because of that. Yeah, because this T2 moved to the left. I don't know. Unfortunately, I don't know by how much to the left compared to this term right here. So I guess
I'm still surprised that the spacing between T2 and T3 increases, though.
Yeah, I'll take it back. I don't know, because you have two terms right here that are a function of I out, right? You have two terms, and the first term is increasing as I out is increasing, but the other term is decreasing as I out is increasing, right? So they're fighting each other basically, right? Now, which one is the bigger is the one who is going to win. So I don't know. I've not done the analysis yet in terms of which one is actually going to be bigger between these two. That would be interesting to actually look into. All right, so that's another thing that I could do for future books. Actually, that's an interesting, what do you call it, analysis to do. So yeah, I don't know. I don't know if T3 is going to move to the left or to the right at this point. You can see we have conflicting terms that, you know, one grows with I out, the other one is shrinks with I out. All right. Okay. Any questions? And the last state, you can see it's even easier to analyze, right? Because it's a constant current through the inductor. That means voltage across the inductor is 0 with constant current flowing through the inductor. So IL is equal to I naught. And then voltage across the switch, which is right here, right? Voltage across the capacitor, I should say, is the same as the voltage across the switch, which is 0, right? So VC is equal to 0, IL is equal to I naught, right? So that will be the two equations for IL and IL and VC. And that will be the end of the analysis for the circuit. The next one is finding the average output voltage. As I said earlier, right? If you can average Vx, voltage across the diode, if you average it, then that's going to be the same as V out. And if you look at the circuit, the states, right? The 4 states, you can see that only 2 states have Vx not equal to 0, right? Here we have Vx is equal to 0. That doesn't matter, right? When you average 0, it's going to be giving you 0. So this doesn't matter. This state doesn't matter for averaging Vx. Same thing with this one. Since Vx is equal to 0, then I'm not going to consider that because average of 0 is going to be 0. Here, though, it's not 0. That one right there is not 0. In fact, this one is equal to Vs. That one is a function of time. It's a linearly decreasing function of time. So therefore, we need to focus on those 2 equations and then average it. You see this? That's the first one, the first state, where Vx is decreasing linearly with time. And then the last state, where Vx is equal to Vs. So when you do averaging, right, as you learn from calculus, right, how do you average a function? 1 over t, 0 to t of the function dt, right? And the limit still is going to be 0 to t, but now there are only 2, what do you call it? You'll break it down into 2 different limits, right? The non-zero ones. That's from 0 to t1, and then the last one is t3 to t2. What happens between t1 and t3? Well, that's 0, right there. That's why I don't include that in the integral, right? So you end up with two integrals, and you carry out the integrals, and then at the end you get this equation right here, and rewrite that in terms of frequency. I get this equation for the average of Vx, which is equal to V out. And that is the exact equation to calculate average output voltage, okay? Supply voltage or input voltage times 1 minus Fs times T3 minus T1 over T2. Is this a buck equation, do you think? Or Boost equation? How do we know this is a buck? That's probably the more correct way to ask. How do we know this is a buck equation?
That's less than 1.
Yes. So if this term right here, right, is between 0 and 1, right? Or actually no, the better way would be this. Let me rewrite the equation. Vs 1 T3 minus T1 over 2 over T. Yes, right there, right? So if I know that this term T3 minus T1 over 2, right, is always less than Ts, right? Therefore, I'm going to have a fraction right here. So 1 minus a fraction gives you another fraction, right? So it's going to be a fraction of Vs if this condition is true. Is that true? Is this always true?
TS can't go below T3 either. So it can only get bigger. So the denominator can only get bigger, and Ts can only go down, right? Oh wait, no.
Well, T3 is always less than Ts for sure, right? So and then you subtract T1 over 2 from a number that is less than Ts. So I know for sure that this is always less than Ts.
Oh yeah, I just got signs mixed up. Bunch of double negatives.
Okay. Yeah, I know for sure that T3 has to be less than Ts. Right. So if this number is already less than Ts, and then you subtract T1 over 2 from that, that's going to be even less than Ts. So that's how I know mathematically that this is a buck equation, because this constant right there would be a fraction. Any questions on that? All right, and then just like the previous circuit, I can do graphical approach for this, right? Estimating the output voltage rather than using the exact equations. I use the graphical method where I have the ratio of the frequencies and the ratio of the voltages with respect to the ratio of the load versus characteristic impedance. So I'll let you go through the look at the derivation I've done for this equation. This is the equation I'm looking for right there. That shows that the ratio of the frequency is a function of the ratio of the voltages, right? V out over Vs, as you can see right there. So every single term has V out over Vs, right? And if I assume a constant RL over Z naught, right? A constant RL over Z naught, then I could have a family of curves or graphs that would be a function of RL over Z naught, right? So right here, if I graph those, graph the equations with respect to a constant RL over Z naught, then I have family of curves, right? That looks something like this. So this is good to approximate the output voltage, right? If let's say you know what the resonant frequency is, what the switching frequency you choose, right? Then you have the ratio of the two. Let's say that ratio is 0.5. Then you go across, right? And then RL over Z naught, right? We know what Z naught is. That's just L over R, L over C, LR over CR. That's going to be a fixed value, right? And then RL, that's the load resistance, right? So per given load resistance, then you get the ratio of RL over Z naught, right? So let's say that that ratio is 0.2, let's just say, right? So once you do the ratio of the frequency, let's say that's 0.5, you go across, right? And then that's the 0.2 right there, intersection of the horizontal line with 0.2, right? And then you go down right there, straight down to give you the ratio of the required ratio for the output voltage to input voltage. So for that case, right, if Fs over F naught is equal to 0.5 and RL over Z naught is 0.2, then you can see that V out over Vs is equal to 0.4, right? So therefore V out is equal to 0.4 times Vs. Again, this is approximation. And typically we know what Vs is. That's how you would estimate output voltage. Any question on this? All right. I'm going to let you do the example. It is similar to what we had in the previous circuit, finding P's, right? T1, T2, T3, and switching frequency, right? And then the peak of the capacitor voltage, and then using the graphical method, right? In this case, I think I'm asking you to find the frequency instead of output voltage. Right? Okay. Any questions? Yes.
So the zero current. Oh, sorry, there's reverb. The zero current had the opposite proportionality with frequency, right? Where as you increase frequency, the output voltage would go down, or it would go up, and then this one it goes down.
Yeah, you're right. Looks like you're
Okay.
right. Is that assuming everything's fixed? Is that what you're saying?
Yeah.
Assuming everything else is fixed. You're looking at the equations, right? Aren't you?
Yeah, and the graphs.
Oh, and the graphs. Oh, I see. Okay. Yeah, because I thought you're looking at this equation right there. If you increase switching frequency, then it's going to get less. Then the fraction is going to get smaller and smaller.
Yeah.
Yeah, you're right. And also you said from the graphical method as well. You see that?
Yeah, because they're both bucks, right?
Mm-hmm.
Like 100% of the time.
Yeah.
Okay.
Yeah. So we increase switching frequency. Increase switching frequency. Oh yeah, you're right. Yeah. If you increase the switching frequency, you get you get less and less ratio. Yeah, very good observation. All right, so that agrees with the average output voltage equation. That means my derivation is good too. Because I've not actually looked into proving whether or not this is algebraically, of course. I did all the algebra, but I might made a mistake somewhere. So that's why I'm asking you to go through the derivations if I miss a term or something. But looks like from the result I have, and I drew the graph from that equation, looks like it's consistent with what you observe from the actual average output voltage equation. So that's good. All right. Let's go to the next one. Before I go there though, the two that we talked about in this chapter, those are just a couple of examples for soft switching, zero current, zero voltage, right? There are more, right? You have the regular, you have the standard buck converter. Then you can have the ZCS. This is the one that I discussed in this class. There is another version of it right there. Right? There's also zero current switching buck. There's more. I'm just showing two examples of zero current switching buck. And for a boost, in case you are interested in doing the boost zero current switching, that's an example of a ZCS boost. And that's another example, different topology, right? But it's achieving the same thing, zero current switching. They're both boost, but they're different topology, as you can see, right? And then we can also have buck boost, ZCS, in case you're interested in buck boost. I'm providing two different examples, two different topologies for ZCS buck boost. Okay, and the same thing with ZVS, zero voltage switching. Right, that's the one that where's the one we cover? Oh, this is the one. This is the one we cover. Oh, no, not that one. Which one did we cover? Oh, I missed the diode. There should be a diode right there. Oh, there should be a diode there. Sorry about that. So please add that. So this is the one that we cover, right, in this chapter. And there's another version of that, which is right here. Right. And then for a boost, there's one version. There's another version of ZVS boost. Likewise for buck boost, in case you're interested. I have two different examples, topologies for ZVS buck boost. So there's a lot out there. Yeah, there's a lot. It's very hard to keep up. People always come up with different ways of achieving ZCS and ZVS. And these are different controllers that you can use to achieve ZCS and ZVS. Okay, to give you some examples, commercially available controllers. All right. Are there any questions before I move to this next one? No? All right. So this next one, if you look at the topology, it's non-isolated, right? But this is actually being used more for isolated topology. How do you convert it into isolated topology? Is by replacing this inductor with a transformer right there. So if you look at the second picture circuit right there, that's the same circuit, same topology, except making it as a isolated topology. So we have the non-isolated version up there, the first picture, and then the isolated version of the same circuit on the second picture, second schematic. All right. Now, so if could please have please have your attention here. The way I'm approaching this next one is different than before. That's why it's important for you to pay attention here to understand how to analyze this circuit. Now, this circuit is, of course, different from the previous one. In the previous one, you have 4 different states. This one as well. This one actually has, it could have 5. But the unique thing about this resonant converter is that in the previous circuit, the 4 states are typically different circuits, right? They're all different circuits. If you can see, this circuit right here looks different from that circuit, right? And that circuit looks different. You know, every single state has a different circuit, right? Now here, you'll see that the four states, the four basic the four main states of this converter, each has the same resonance circuit. The one thing that makes each of the states different is the way we connect the input voltage to the resonant tank and the output voltage to the resonant tank. I'll talk more about it next. Now, hopefully that becomes clear after I explain how I can divide the circuit into 3 different stages. The first one, look at this stage right here, right? That's the middle stage. I'm going to start with input stage. This is what I call the input stage. And then I have the output stage right there, right? And then in the middle, right there, I have what I call resonant tank, right? And you can see that in the resonant tank right there, I have L in series with a capacitor. That's why it's called series loaded resonant converters, because L and C are in series with the load. That's the load, right? They're in series with the load. Okay. Now, if you just focus on the LC tank right there, right? And then I'm going to erase the input here and the output there. You can see that the input to the tank right here is connected by these 2 wires, right? One is called A, node A, the other one is node B, right? On the input. So on the input side of the tank, they're connected through AB terminals, right? And then on the output is connected through B prime and B terminal. See that? The 2 wires standing right there. Okay, any question on that first? Okay, now I'm going to erase that because it's going to get crowded soon here. All right, now if let's say you place those switches, right, and the diodes, and those switches T plus and T minus, those are unidirectional switch, meaning the current can only flow downward. If you look at T plus, current can only go top to bottom side of the switch, right? So current can only flow this way. Same thing with T minus, can only go this way, right? Unidirectional. Diode, I don't have to say it, it's also unidirectional, right? It's upward for both D plus and D minus. And the diodes on the output, that's a rectifier. You can see that's a full bridge rectifier. This resonant, as you know, will give you a sine wave, right? So the voltage across B prime and B is going to be sine wave, and that sine wave is going to be rectified, fully rectified by this bridge rectifier, and it gives you DC on the output. And then you average it by this capacitor, all right? Now, so far, any questions? What I just said? Okay, if not, okay. Now, if I look at the tank, right, the LC right here, if I call current through the inductor, right, current through the inductor is the same as current through the capacitor. If I call positive, if I say that positive current flows into the circuit, I'm going to define that positive direction to be the direction of the current from left to right, just like this arrow shows you. So whenever I have current flowing from left to right, I'm going to call that positive current as a reference. If it's the opposite, current flows from right to left, then it's going to be negative, right? Is it possible for the current to go positive, negative? The answer is yes, because remember, this is resonant, right? Resonant means sine wave. If I allow the sine wave to go negative, right, that means it is possible for this current to go negative as well. Positive, negative, right? So 2 different possible directions of the current if we allow them, right? Positive, negative. Now, for positive current, look at the input stage first. So please pay attention. This is the important part. For positive current, meaning what? Current flow from left to right. Can you tell me the two different possible ways to get positive current from the input stage? I have 4 different switches, right? T plus, T minus, D plus, D minus, right? Well, I'm gonna tell you the first one, that I can get the positive current from T plus. Imagine if T plus is on, right? Then I could have positive current flowing through T plus and goes that way, right? Assuming the other ones are off. Agree? So that's one possibility, right? Can you tell me another possibility of where positive current may come from?
D minus is on.
Minus.
D minus is on, exactly, very good. So when D minus is conducting, then it will give you positive current. I think you got it now. So then if I do the opposite, negative current, then you can see that negative current through the tank, right, meaning current going to the left, can only flow through D plus or T minus when T minus is on. Agree? So those are the different conditions. Any question on those? No? All right. Let's look at, well, let's stay in the input first. What happens when we have T plus is on, right? That means a positive current. What's going to happen with voltage across the input? What is the input voltage across the tank? What is this voltage right there, AB? What is VAB when T plus is on?
VD over 2.
Yes, exactly. So if you follow the current, right, current must flow into the tank and then coming back this way, right, through the bottom branch, and it goes into the B, right, and it makes the big loop this way, right? So you can see that if that is the case, let me just erase this. I'm going to do this slowly. So it makes this loop. Right, like that, like this. So you can see that the input to this resonant tank is equal to VAB. That's going to be equal to VD over 2 plus VD over 2. You agree with that? So A, because this is a short, is equal to that node, this node right there, right? That's plus of the VD2. And then B is equal to the negative of VD over 2. So we know that across AB must equal to VD over 2. Is that clear? Let me know if you have any questions. All right, so that's what happens when T plus is on. So the input voltage to the tank when T plus is on is equal to plus VD over 2. What happens if we have positive current still, right? Current is positive, but instead of T plus, D minus is the one that's conducting the current, the positive current. So it goes this way, right? Right there, making this loop. So what is VAB at this point? If the positive current is being supplied by the D minus, then you can see that voltage at the input of this tank changes, right? VAB is now, see, A, VD. Exactly, see A right there is connected to the minus side of the VD, and then B is connected to the positive of VD, so it's actually flipped. So it's minus VD over 2, right? Okay, and you can do the same thing with D plus and T minus. I mean, we can do it quickly. I know we're almost running out of time, but you can see that if T minus is on, what is VAB equal to for negative? So negative current. So T minus, that means it's going to go down, right? So that's going to be negative again, right? T minus on, that means current flows this way. So that's negative on the A, positive on the return, right? So that's going to be minus VD over 2. And then for D plus, right? That's the last one. For D plus, what is VAB equal to? So again, that's for negative current. negative current, D plus on, so negative goes this way. So it's going to go up that way and return this way, right? So you can see that A is now equal to plus, and B is equal to minus. Sorry, B right there is equal to minus. So now it's going to be plus again, right? So you can see that depending on which device is conducting, that will determine the input voltage to that tank. That's the model behind that, this story. Now, let me finish this and then we can adjourn. The same thing goes with B prime and B. I'm not going to go through this slowly, but you can see depending on whether or not the current is positive or negative, watch what happens when current is positive. When current is positive, it goes this way, right? So what is B prime B equal to? That's going to be plus V out. See that? If current is positive, then B prime B is going to be plus V out. That's when the current is positive. What about when the current is negative? Okay, one more time and then I'm done. Because I don't want to stop right before this is done. So when the current is negative right there, that means it has to come from this diode right there, right? And then this way, that way, and then this way, and then that way. Right, so current is negative, so it goes this way, up, down, but that way, right? Notice if I have negative current, look at what VB prime B is. This is VB prime B. When the current is positive, it's plus V out. When the current is negative, you can see that B prime B is equal to minus V out, isn't it? B prime right there is connected to the negative of V out. The B node is connected to the positive of V out. So it's flipped, right? So again, the moral behind this analysis is that the polarity of the output of the tank would depend on the direction of the current, right? And then before we adjourn, you can see that by doing so, now I can summarize what we just did. That circuit, I can model that circuit as the following. You have LC in series, and the input could be either plus or minus VD over 2, depending on which device is conducting. And on the output, it could be either plus or minus V out, depending on whether or not the current is positive or negative. Right? So now you can see that we can come up with a simpler model of the circuit. It will be easy to analyze than having the initial circuit, right? So this is a much simpler model than the actual circuit. But hopefully this makes sense, that the input to the tank can flip back and forth between plus to minus VD over 2. The output could flip back and forth between plus and minus V out, depending on the direction of the current.